In this lesson, we're going to look at a really neat topic called dimensional analysis. There will be two messages of this lecture. The first one is that if you write down an equation or a mathematical model for a natural system, then it needs to be dimensionally homogeneous. What that essentially means is that the units of the equation are consistent. So we'll talk through examples of that first, and then we'll look at how dimensional analysis can actually lead to the creation of models. So we'll follow an algorithm and re-derive some fundamental equations in physics. Okay, let's first talk about what it means to be dimensionally homogeneous. So of these three equations, which have consistent units? Where are the units balanced? Are there any examples where the units are not consistent and it doesn't make dimensional sense? Okay, so the first one is distance equals speed times time. So here I'm just imagining I'm driving a car straight down a road. How far you go is how fast you were going times how long you were driving. Let's make sure that those units make sense. I don't know if I'm measuring here in feet or meters or miles or what have you. Let's just say meters. So let's suppose I measure distance in meters, speed then in meters per second, and time in seconds. On the left-hand side, we have meters. On the right-hand side, we have meters per second times seconds. That cancels out to meters. So overall, the left and right-hand sides of this equation both have units of meters. When we do this kind of analysis, we assume that we measured well. For example, I didn't do distance in feet, speed in meters per hour, and time in minutes or something like that. So you don't have an issue here of using different systems. Rather, once you've picked a system, do the units make sense? Okay, imagine you take a ball and you throw it straight up. You give it an initial speed of v0 meters per second, and you're throwing it from height h meters. We have this well-known parabola degree 2 equation for the height over time of this ball. So h of t is the height at time t. When you plug in 0, you get that initial height of h. This is a well-known famous equation. Let's make sure that it's dimensionally homogeneous. So on the left-hand side, height at time t is meters. On the right-hand side, my first term is -1/2 times gravity times t squared. -1/2 is just a number. Gravity is an acceleration, so that's meters per second, or in other words, it's meters per second squared. Right, so that's like your velocity per second, so meters per second, and then time is seconds squared. Okay, that looks good because that would cancel out and give us meters. The second term is the initial velocity, so that's meters per second, and then times time is seconds. So again, that cancels out and leaves us with meters, and then the initial height m was also meters. So all four pieces of this equation have a unit of meters, so this is also dimensionally homogeneous. So we get yes and yes. What about the third equation? I just made this up. Cooking time equals temperature times volume. Well, cooking time, let's say that this is measured in minutes. Temperature in degrees Fahrenheit. And volume, now volume, you think of it like 4/3 pi r cubed for a sphere, or x times y times z for a rectangular cube. So if I have a baking dish that's like a rectangular cube, it would be the width times the length times the depth. So that could be like inches cubed, or centimeters cubed, or kilometers cubed, whatever your volume refers to. So on the left-hand side, we have minutes. On the right-hand side, we have a temperature degree and inches cubed. This is not dimensionally homogeneous. Again, I just made that equation up, so don't try to use it for cooking. Our three fundamental quantities are mass, length, and time, MLT. If you're trying to remember that later, if you've seen The Princess Bride, it's like MLT is a mutton, lettuce, tomato. Here it's mass, length, and time. I like to think of this like your three principal colors, and then with those colors, you try to mix all the other colors. Same story here. So what we would like to do is take other quantities and interpret them in terms of some amount of mass, so mass raised to some power, length raised to some power, and time raised to some power. So we'll run through all these examples to get that. What we do when we express a quantity in terms of its MLT decomposition is we put that in square brackets. So for the concept of velocity, we'll say in square brackets v equals, and then on the right-hand side, we'll give m to some power, l to some power, t to some power. So that's what the square brackets is indicating, is how we should view this quantity in terms of these fundamental dimensions. So velocity is something like meters per second or miles per hour. So that's a length divided by an amount of time. You could write L over T. But how I would like to do that for this exercise is m to a power, L to a power, T to a power. So that's going to be m to the 0, L to the 1, T to the negative 1. Acceleration is meters per second, or in other words, meters per second squared. So that's like a length divided by a time squared. But that's not how we want to write this. We want to write this as m to the 0, L to the 1, T to the negative 2. Okay, for density, it might help to know that density is mass divided by volume. So the form for density is going to be the same as that for m divided by v. So we can make that substitution. M is just mass. Volume, again, is a length cubed. You can think of that like 4/3 pi r cubed, or for rectangular cube, x times y times z, as we already discussed. It's your length measurement done 3 times. So that's length cubed. So overall, this is going to be m to the 1, L to the negative 3, T to the 0. If you step on a scale in the United States, you're going to get your weight in pounds. So when we see pounds, that's a measurement of weight. If you get on a scale in Europe, it's going to be in grams, which is actually a measurement of mass. They're not exactly the same. Weight is actually the force that gravity exerts on your mass. So a measurement of weight is really a measurement of force. It's like your mass times gravity. That's really a type of acceleration. So this is going to have the same breakdown as mass times acceleration. Acceleration we did 2 lines above. Now we multiply that by mass. So overall, this is going to be m to the 1, L to the 1, T to the negative 2. It's the same story with force. Force is mass times acceleration. So it's m to the 1, L to the 1, T to the negative 2. For energy, if we think of kinetic energy, the formula for kinetic energy is 1/2 mv squared. So I'm going to write 1/2 mv squared. Of course, there are other types of energy. There's potential energy, for example. But energy is going to be dimensionally consistent. So if I can do it for kinetic energy, then I know what the breakdown is for energy. 1/2 is just a number. Mass is mass. V squared is the velocity squared. Velocity we did on the first line, so it's now going to be multiplied by m, so we get m to the 1, L to the 2, T to the negative 2, because we squared that velocity. Work is force times distance. Force, we said, was m to the 1, L to the 1, T to the negative 2. Distance is just going to give us another length measurement. So overall, this is going to be m to the 1, L to the 2, T to the negative 2. Okay, power is energy per time. So this is going to be like E divided by T. So to our energy up here, we're going to increase that negative exponent on T from T to the negative 2 to T to the negative 3. So this is m to the 1, L to the 2, T to the negative 3. Pressure is like force per unit area. So we'll take force and divide it by area. Force was m to the 1, L to the 1, T to the negative 2. Just like volume is L cubed, area is L squared. So when we take this and divide it by L squared, we'll end up with m to the 1, L to the negative 1, T to the negative 2. Let's look at some more examples of equations and determine if they're dimensionally homogeneous. So this time we'll do it in terms of ml and t. Let's start with the famous equation E equals mc squared. E is energy, m is mass, c is the speed of light. So on the left-hand side, we have E, which we just found to be m to the 1, L to the 2, T to the negative 2. Notice here I don't have to worry about the actual units I'm using. This is an expression in terms of fundamental quantities. On the right-hand side, we have mc squared. That's a mass times a speed squared. So mass is going to give us m to the 1, and then speed is length per time. So squaring that is going to give us L to the 2, T to the negative 2. These two sides agree, so yep, we're good. Next one is just volume of a sphere of radius r. Kind of mentioned this with volume already, so yes, it is dimensionally homogeneous. On the left-hand side, we have m to the 0, L cubed, T to the 0. And then on the right-hand side, let me write 4/3 pi r cubed in square brackets. 4/3 is a number, pi is a number. These are dimensionless quantities, they're just numbers. So this is equivalent to finding the dimensional analysis for r cubed, which is the same as on the left, so that's m to the 0, L cubed, T to the 0. For the third example, this is a true equation when we're working in meters and meters per second. But I want to just point out here that you have to be careful when you do something like plug a number in for g if you're trying to state a general formula. So on the left-hand side, our height is just a length scale. So that's m to the 0, L to the 1, T to the 0. I would get the same breakdown for the initial speed times time and the initial height. But when I look at that leading term and do the analysis for negative 4.9 t squared, if I've written this as negative 4.9, that's now just a number. So this is actually going to be the same as t squared, which is m to the 0, L to the 0, T to the 2. Now, of course, this formula is still going to give you the correct answer. But written this way, it's not dimensionally homogeneous. We would need to take 4.9 and replace that with g over 2. So there we would pick up the correct dimensions. As we saw in the previous slide, plain old numbers, like pi or 4, are dimensionless. You could write that as m to the 0, L to the 0, T to the 0, or you could say, hey, that's just 1. So you can write square bracket pi equals 1. Let's talk about some other dimensionless quantities. Percentages are dimensionless because a percentage is a part per whole. And the part and the whole have been measured using the same unit. So it could be like I've run 4 kilometers out of 7 kilometers. Or more likely, I've eaten 4 cookies out of 7 cookies. But once you set up that ratio, you have a ratio of like quantities, you're left with no dimension. So if you're trying to analyze something like 10%, you would say that's m to the 0, L to the 0, T to the 0, or just 1. The next one is interesting because two angles, we often associate a unit. So people sometimes feel that there is a dimension with angles. But what I'm about to say is true whether it's radians or degrees. Angle measurements are dimensionless. There's a reason for it. If you have, say, an angle opening up in some circle like this, say L is the arc length enclosed by the two rays of this angle. Then we know that circular proportions give us that the ratio of theta to 2 pi is equal to L divided by the circumference 2 pi r. I'm working here in radians, but it would be the same story in degrees. We cancel out the 2 pi, and we're left with theta is a ratio of the arc length to the radius. Those are both length measurements. So since theta, the angle, is a ratio of a length to a length, theta is a dimensionless quantity. If you're looking at an equation and there's something like sine of theta or cosine of theta, those are also dimensionless. That's because sine, cosine, tangent, these are ratios of sides on a triangle. So we got SOHCAHTOA. If you write sine of theta is the opposite side divided by the hypotenuse side. Again, that's a length divided by a length. So that's a dimensionless quantity. Okay, now we finished the first part of this lecture, which says that an equation needs to be dimensionally homogeneous. Now we're going to use this principle to actually take fundamental quantities, which we know are related, like distance equals speed times time. Distance, speed, and time are somehow related. And we're going to show how you would derive this equation just using dimensional analysis. This is a really neat technique. You can kind of re-derive fundamental laws of physics through dimensional analysis. Okay, so there's a lot of words on this slide. We have a theorem and then a procedure. So what we will do is look at the big picture here, but then as I work through a couple examples, I hope you'll see how to do it in practice. So our methodology comes from the Buckingham Pi Theorem, which says that an equation, like E equals mc squared, is dimensionally homogeneous if and only if it can be written in the form f of pi 1, pi 2 through pi n equals 0, where pi 1, pi 2 through pi n is a complete set of dimensionless products. Now, if you're seeing this for the first time, you have no idea what I'm talking about. I didn't either. The theorem really probably should be stated after we go through a couple examples. But here's what we're going to do. So we're going to put this into practice. And again, once you see a few examples of how to do this, I think it becomes clearer. But what we're going to do is take some principle, like distance, speed, and time are somehow related. And we're going to first find all of the factors that we think affect a system. So when I say find the m factors, variables, and parameters that affect the system with dimensions, I'm going to find the terms like distance, speed, and time. I don't need to have a relationship between them. In fact, the relationship is what we're trying to get to. Okay, so that's the first thing to do is identify what matters. Then we're going to do a little linear algebra. This could be complicated, but we're going to end up looking at the same story every time. But we're going to create a matrix that stores the dimensional information for the factors that we identified. Then we're going to do what's called row reduction on our matrix, identify the rank R, and we'll end up solving something with that matrix to determine the set of dimensionless products. Now, in theory, how many dimensionless products will we have? The difference between the number of factors we started with and the rank R of the matrix. This will always be 1 for us. Not in general, but for us, it will always be 1. Okay, so basically, we're going to end up with 1 dimensionless quantity, and that's going to lead to our relationship. So then we apply Buckingham's theorem. We just say that there exists an f for which, in our case, f of pi 1 equals 0. From getting to write that down, we can then come up with an equation which might be a fundamental equation of physics. Okay, so what we're going to do is look at a few examples of this methodology coming out of this theorem and work out, how to do this in practice. For us, we're not going to look at them as general cases. We're always going to have certain simple arrangements come out of the calculation. Let's start with the three quantities I keep mentioning: distance, speed, and time. What we're going to conclude is basically a version of distance equals speed times time. So we don't know this yet, but suppose that we know that there's a relationship between distance, speed, and time. Okay, so step one is just to identify the players involved and find the dimensions of them. So distance is a length measurement, so that's m to the 0, l to the 1, t to the 0. Speed is going to be like meters per second, so that's a length divided by time, so that's m to the 0, l to the 1, t to the negative 1. And then time, of course, is time. Okay, I think step 2 is kind of fun. We're going to organize these into a matrix. So our matrices are always going to have 3 rows, and I'm going to label the rows M, L, and T outside of the matrix. Okay, so those are the 3 rows of our matrix, and then the columns are the quantities that we found in number 1. So I'm going to label the columns D, S, and T. Okay, now what we do is take the exponents here and just say, hey, D was 0, 1, 0. So D was m to the 0, l to the 1, t to the 0. S was m to the 0, l to the 1, t to the negative 1. T was 0, 0, 1. Let's call this matrix M. What we need to do now is row reduce M, and luckily we'll be able to do this in MATLAB. So let me write that we need to ref M, and then I'll open up MATLAB and show you how to do that. I'm in MATLAB. You could also be in Octave. We're just going to need the command window. We don't need a script file here. What I'm going to do is make my matrix. So I do M equals square bracket 0, 0, 0, spaced apart like that, or you can separate them with commas. And then to go down to the next row, I do a semicolon, and the next row of our matrix was 1, 1, 0. And then the third row of the matrix was 0, negative 1, 1. Close off that square bracket. I'm not going to suppress output because I would like to look at it. Okay, so there's our 3 by 3 matrix, and if the numbers are wrong, everything will be wrong. So it's worth checking number 1 carefully and then also making sure your matrix looks good. Okay, so that's our matrix. Now what we do is just ref of M. So this is a command in MATLAB, and this is going to put M in what's called reduced row echelon form. Okay, so let me write this down on the slide, and then I will put MATLAB away because this is all we need for MATLAB. So our reduced row echelon form has columns that look like 1, 0, 0, 0, 1, 0, and then 1, negative 1, 0. As I mentioned, for us, we're not going to need what I'm about to do because it's always going to work out to give us just one product, pi 1. But the rank of this matrix is the number of leading ones. So that's 2. So just to give you a glimpse of what the full story would be if we did more equations, we would now say the rank of this is 2. That's actually the rank of M. So the rank of M is 2. If you flip back to the methodology for a second, we started with M equals 3 factors. We found the rank to be 2. So we're looking for 3 minus 2 equals 1 dimensionless products. So since 3 minus 2 equals 1, we just need a pi 1. Okay, so let's find out what pi 1 is going to be. Pi 1 is going to be some product of d, s, and t. So we will write pi 1 equals d to some power, s to some power, t to some power. I'll call those powers p1, p2, p3. So pi 1 is d to p1, s to p2, t to p3. And then what p1, p2, p3 satisfy is that the second matrix we wrote down times the vector p1, p2, p3, where we just do matrix multiplication, needs to equal 0. This is going to give us a system of equations for the unknowns P1, P2, and P3. So if I do my first product, I get 1P1 plus 0P2 plus 1P3 equals 0. If I do my second row with the column, I'm going to get 0P1 plus 1P2 minus 1P3 equals 0. And then the third row doesn't give us anything, that's just 0 equals 0. This is a system of two equations for three unknowns, which means we can't solve it using something like substitution or elimination. What we're going to do is say, put P1 and P2 in terms of P3. So this first line tells me P1 equals negative P3. And the second line tells me P2 equals P3. Then you just pick a number for P3 and solve for P1 and P2. Don't pick 0. You don't want to get 0, 0, 0. That would be kind of pointless. Usually I pick 1. If I've got something like a half in there, I might pick 2 to make the numbers nice. Let's set P3 equal to 1. So then P1 is negative 1 and P2 is 1. Okay, we can plug that back into our expression for pi 1. We get that pi 1 is d to the negative 1, s to the 1, t to the 1. And then we can simplify that. This is just going to be st divided by d. Okay, the next step is a little bit strange. I hope you see how to use it in practice after we've done a few examples of this. But what we're going to say is, thanks to Buckingham's Pi Theorem, we know that there's some function out there, I'll call it f of x, for which if I plug in pi 1, in other words, if I plug in st divided by d, I get 0. I don't know what that function is, but we're going to say, suppose its root is called c. That means st divided by d must be equal to that root c. Now we just rearrange terms into a form that we like, so we could then bring d over. I'm going to write d times c equals st. And that's as far as this process will take us. So we've now got that there's some constant c out there for which d times c equals s times t. That's not exactly d equals st because it didn't tell us that c equaled 1. And I should also mention that it doesn't tell us how many roots there are. So I'm saying, suppose there's one root called c, and then we get this equation because I know where I'm going with this calculation. And for us, that's what we're going to do. Turns out c is 1. So then we get distance equals speed times time. So how would you find 1? Perhaps you would use data or something like that to deduce that the constant should be 1. So really what this algorithm gives us is like a proportional relationship between distance, speed, and time, so that we can see how those quantities would have to be arranged within an equation, and then there might be a little bit more work to do beyond that. Okay, I think once you get the hang of this, this is really fun. Let's look at a couple more examples. Okay, now we're going to derive an equation, which I've already given us here. So the goal is to get back this equation. Well, let's derive the equation for the drag force due to air resistance experienced by a free-falling object like a skydiver who hasn't yet opened their parachute. This is what we're essentially going to end up with, something that looks a lot like this. Let's do this process now to get there. So if we are trying to come up with this for the first time and we're thinking about how objects fall to Earth, the first thing we need to do is identify the quantities that matter. We would say, okay, there's some air resistance, that's a force. We know that the breakdown for force is m to the 1, L to the 1, t to the negative 2. What else matters? The thickness of the air, that's the density. How the object is hitting the air, that's given by the area. And also how fast you're traveling, because the faster you move, like the faster you try to run in water, the more resistance you feel. So your velocity matters. If you're moving very slowly, you don't feel as much resistance. Okay, so if we go through those quantities as well, we get that density, as we already found, is m to the 1, L to the negative 3, t to the 0. Area is like a length squared calculation, so that's m to the 0, L squared, t to the 0. And the last quantity is the velocity. for which we know it's m to the 0, l to the 1, t to the negative 1. Okay, let's make our matrix. It's going to have 3 rows for m, l, and t, and 4 columns for the force, the density, the area, and the velocity. Okay, our force powers are 1, 1, and negative 2. Our density powers are 1, negative 3, and 0. For area, it's 0, 2, 0. And then for velocity, it's 0, 1, negative 1. Okay, now I'm going to open up MATLAB Online, put this matrix in it, and then take the RF form. Okay, so we have M is the first row, 1, 1, 0, 0, semicolon to go down to the second row. Then we have 1, negative 3, 2, 1, semicolon down to negative 2, 0, 0, negative 1. Okay, that looks good. That's our matrix. And now we just ask MATLAB for the reduced row echelon form. So RF of M. I'm going to write this down on my slide and then we'll switch back to it. So RF of M is going to have the first 3 columns that look like 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then the third column is a half, negative a half, negative a half. Okay, let me put MATLAB away and we'll go back to our calculations. The rank of this matrix is the number of leading ones on each row. So we have 3 leading ones like that, so the rank is 3. We started with 4 quantities. 4 minus 3 is 1, so we're just looking for a pi 1. Okay, so if this was the second step of our process, the third step is now to write out what pi 1 should look like. So pi 1 is going to be f to the p1, rho to the p2, a to the p3, v to the p4. And now I get those numbers p1, p2, p3, p4 by solving the system of 3 equations for 4 unknowns that we get out of this RF form. So in particular, we're going to have p1 plus 1/2 p4 equals 0. So let me just go ahead and write p1 equals negative p4 over 2. Similarly, p2 minus p4 over 2 equals 0. That's from the second row of the RF form. So we can write p2 equals p4 over 2. And then similarly, p3 equals p4 over 2. Okay, so each of these relationships came from taking this matrix and imagining what it would look like to multiply it by the vector p1, p2, p3, p4, and then set that equal to 0. So the first row tells us 1p1 plus 0p2 plus 0p3 plus p4 divided by 2 equals 0, etc., etc. Once again, we have 3 equations with 4 unknowns. I'm going to let p4 equal, how about 2? Because we've got all these division by 2's. So let me say, sorry I'm running out of room here, but let's let p4 equal 2. When we do that, we're going to get pi 1 equals the force raised to the p1 power, but p1 is now negative p4 over 2, so that's negative 2 over 2, so that's negative 1. And then rho, the density to the p2, which is 2 over 2, so that's 1. And then same thing for the area, that's area to the 1. And then for the velocity, it's raised to the p4, so that's going to be velocity squared. Okay, now we do this sort of strange end of this process, where we're going to say that based on the theorem, we know there's some function out there, which is a function of one input, for which f of pi 1, in other words, f of fd to the negative 1, rho to the 1, a to the 1, v squared equals 0. So on the one hand, this is the form a root takes. On the other hand, the root of a function is just a number. So if I set that equal to some constant, let's let k be a root of f. Then we get that number k has to be equal to this special form of the input that we're plugging into f. So in particular, I can write it like that. K equals rho a v squared divided by fd. Rearrange terms a little bit, and you get fd times k equals rho a v squared. That's not exactly the form of the equation at the top, but you see what happened here is we get out the balancing that we need to do between the drag, the density, the area, and the velocity. So in particular, we have the drag due to air resistance on one side of the equation, and then rho times a times v squared on the other, where we know that v squared is the correct notion there. Otherwise, how would you know that it should be the power 2, right? So we get the powers that each of these quantities needs to appear in this equation, and then we know that there's some constant that's going to make those two sets of quantities equal to each other. In this form, we have just k on the left. In the form at the top, we have c over 2 on the right, but those are just constants. So we get how to set up this equation relating the drag force to the product of the density, the area, and the square of the velocity. Okay, we'll finish with this example. We want to find the period, or the oscillation time, the time it takes the pendulum to swing one way and back, of a pendulum of mass m and length L, and which is existing on Earth, so there's a downward force g due to gravity. Okay, so let me draw a picture. We have, let's say, the pivot for our pendulum, and then we're going to imagine that our pendulum isn't swinging too wildly, so we have something kind of like a grandfather clock. So here's the pendulum. It has mass m, and its length is L. And usually how we track the motion of a pendulum is we track the angle it makes with the downward. So this angle here would be like theta. And then it's experiencing a force downward due to gravity. And that's all the information we have about this pendulum. Theta, as we already know, is dimensionless. So what are our dimensional quantities here? The length, the mass, gravity, and then also the period itself. We're trying to find a relationship between the period, the length, the mass, and gravity. So those are our 4 quantities. Let's start with a period. We'll call it lowercase t for time. And of course, that's going to be m to the 0, L to the 0, t to the 1. That's a unit of time. Then we have L, that's a length measurement. So that's m to the 0, L to the 1, t to the 0. The mass is a mass. So that's going to be m to the 1, L to the 0, t to the 0. And then for gravity, the force acting on the pendulum is actually m times g. So the overall force is m times gravity. So that's going to be m to the 0, L to the 1, t to the negative 2. In other words, the unit that we typically associate with gravity is meters per second squared. So that's L over t squared. I just realized I've been calling my matrices capital M for matrix. I hope that's not confusing. It has nothing to do with the mass. It's just the name of the matrix. If you'd like, I can change that to, say, capital A. Capital A is often the name of a matrix. Okay, so the 3 rows are going to organize the quantities m, L, and t. And then for each column, I'm going to do t, little l, little m, and g. Okay, so the exponents for t were 0, 0, 1. For L, it was 0, 1, 0. For little m, it was 1, 0, 0. And then for gravity, it's 0, 1, negative 2. Let's put this in RF form. Okay, so I'm going to clear what I did previously. CLC, capital A is going to be 0, 0, 1, 0. You can actually hit enter if you like to go down to the next line. 0, 1, 0, 1, and then 1, 0, 0, negative 2. Okay, let's make sure that looks right. It does. So then we say, what's RF of A? And I'll write this down. If you're familiar with linear algebra, you won't be surprised to see that the RF form is really just swapping the first and third rows, but that's beside the point. So let me go ahead and copy this down, and then I'll switch back to the slides and we will finish this problem. Okay, the rank of this matrix is 3. We started with 4 quantities, so 4 minus 3 is once again 1. That's what we would expect in this course. Okay, so that was step 2. Let's find step 3. The form of pi 1 is going to be the period time to the p1, the length to the p2, the mass to the p3, and gravity to the p4, where those exponents satisfy the equation. Here, I'll go ahead and kind of write it out. So if I go along the first row, that's 1p1 plus 0p2 plus 0p3 minus 2p4 equals 0. Along the second row, it's 0p1 plus 1p2 plus 0p3 plus 1p4 equals 0. So p2 plus p4 equals 0. Along the third row, it's just going to be p3 equals 0. It turns out there's not going to be any dependence on mass in this problem. So for the variables that we have left, p1 is 2p4 and p2 is negative p4. So if I set p4 equal to 1, we get that pi 1 is going to be t to the 2 times 1, l to the negative 1, m to the 0, p3 was 0, and then g to the 1. For the last step, there exists some function of one variable for which pi 1 is a root. Let's call that root c. And we get that pi 1 has to be equal to some constant. In other words, c equals t squared g over L. The question we were asked was to find the period, find that oscillation time. So now if we solve for t, we get that t is going to be the square root of CL divided by G. And again, that's as far as our process goes. It doesn't tell us exactly what C is, but if you're curious, it's actually going to be the way it's written 4 pi squared, because this works out to be 2 pi times the square root of L over G. So our dimensional analysis doesn't take us as far as that, but it does give us how T has to relate to L and G, the kinds of expressions that we need to see in this equation for this oscillation time.